All right, this is the first time I'm chairing my own paper, so you all have to come up with questions. So now Landon will talk about our work on reasoning about under-approximation.
Hi everyone, my name is Lang Liu. I'm a PhD student at Illinois Tech. Yes, this is the joint work with my advisor Farzaneh and Limin from CMU, Gabriel and Mark from SEI. Nowadays, formal methods are drawing attention because critical systems demand strong guarantees. It results in many verified software like CL4 and the verified TLS implementation. If all the components in the system are verified, then we say the whole system is verified. But for large software like Chrome, it has more than 30 million lines of code. So fully verify it seems unrealistic. So instead, large systems usually use many tested components. For example, an operating system may combine the verified CL4 with many tested device drivers, while a browser may combine the verified TLS with many tested components. The question is, can we compose those tested behaviors and then declare the system satisfies all of them? The example on the next slide shows the answer is no. In this example, say we are testing a window. The handyman number 1 comes on a sunny day above freezing. He opens and closes the window. No screeching noise, perfect. Then handyman number 2 comes on a cold morning below freezing. He checks for condensation. The glass is clear, no fog, no problem. We need to notice that those behaviors are only tested to work under some conditions, which is an under-approximation. So we call them under-approximated analyses. Comparatively, verification checks all possible conditions, which is an over-approximation. Here, each testing looks great, but can we compose them and say the window works well in general? We need to notice that the intersection of the two conditions yields an empty set. So the empty set means the two testing results never shown to hold at the same time. So the composition does not make sense. The window may still start squeaking or fogging again. Here we show the problem of composing testing analysis. Composing testing with verification adds extra complexity. Our goal is to design logical foundation to reason about the composition of heterogeneous analyses. I will show you how to formalize our idea with another example. By quantifying under-approximation with another example. The example is a space launch vehicle called Ariane 5. It reused two components from its predecessors, Ariane 4. The IRS, inertial reference system, and the OBC onboard computer. OBC has two variables as its internal resources, LT, the launch trajectory, and temp, the internal temperature. Those two components work together. OBC calculates and sends HV, the horizontal velocity, to IRS. IRS then calculates align, the alignment data, and then send it out. These two components were tested to work well in Ariane 4. However, with assuming those testing results from Ariane 4 and directly reusing those components, the first flight of Ariane 5 failed. Ariane 5 has a different launch trajectory that results in a much higher HV. The HV cannot be stored in a 16-bit side integer in IRS. An exception was sent out after an operand error happened in IRS. The exception was not handled properly, finally leading to the failure. The lesson is we should never treat under-approximated analyses as if they were analyzed under all possible conditions. To prevent situations like this, we propose to quantify the level of under-approximation via a modality. It ranges over the component's internal resource values. For example, here, the analysis on OBC in Ariane 4 only consider the cases where the internal value of LT is less than some V0. So we attach this modality to the guarantee of this analysis. It shows that this guarantee does not work for Ariane 5 because Ariane 5 has a different LT that is not covered by the test cases here. More importantly, this modality enables us to soundly compose differently analyzed components. I will show you how to formalize our idea and what the main challenges are with two analyses from Ariane 4. In the first analysis, it establishes that the HV is positive and within 16 bits and the right side of the turnstile. And the left, it makes two assumptions on the output HV. Let's assume the HV is tested to be positive when temp is greater than 0 with any LT. HV is also tested to be within 16 bits when LT is less than V0 with any temp. We quantify these two assumptions with two sets. They are the modalities we mentioned earlier. They describe the condition under which those assumptions are tested to work, those behaviors. So we call them test levels. I think we all agree that the guarantee only holds for the intersection of the two sets. We call the intersection T1. In this way, test level quantifies the level of under-approximation. And to make it more interesting, I will show you another analysis that works on disjoint resources. For that, we add an additional component, SNS, the sensor. It sends ENV, the environmental data, to IRS. This analysis is on the component IRS. It makes two assumptions on its two inputs. First, there is an input ENV, no matter what its value is. Second, the input HV is positive and within 16 bits. Then this analysis declares that the output align will not be an exception. Assume assumption 1 is established by a verification, so it works for all the possible internal resource values of SNS. We note this as max SNS, which is the test level for assumption 1. From the last slide, we know the test level for assumption 2 is T1. So what's the test level for the guarantee here? This time, an intersection does not make sense anymore because max SNS and T1 apply to disjoint resources. So instead, we use a disjoint union to compose them. However, this is still not enough. From the system diagram, we can see the value of align also depends on IRS. So we also need to consider the internal value of the test level for the internal value of IRS. Assuming this analysis is a verification, so again, we note this as max IRS. The test level for the guarantee turns out to be the disjoint union of max SNS, T1, and max IRS. Now, we have observed two ways to put assumptions together. In the first judgment, both assumptions are describing behaviors that rely on resources of the same component, the blue OBC. But in the second judgment, the two assumptions are describing behaviors that rely on disjoint resources. But despite these two different interpretations, we put them together using the same separator. We need to find a way to unify these two interpretations. To give you a better analogy, the first interpretation is similar to the regular conjunction in separation logic. It talks about the same heap. But the second interpretation is similar to the separating conjunction. It works with two disjoint heaps. It turns out there is a nice logical foundation that can help with this unification. It's called the logical bunch implication. I will give you some background and show how we build our system on top of it. The logical bunch implication was proposed by O'Hearn and Pym in 1999. It merges intuitionistic logic and multiplicative intuitionistic linear logic. In BI, formula borrows connectives from both sides. Its context has two separators. As shown in the example, the semicolon context with the same resources, while comma for disjoint resources. We say we use test level to quantify the level of under-approximation. To achieve that, we need an additional layer on BI. So we extend the atomic formula BI to capture component behaviors. Now it is the predicate PX, where X is the message along channel C. The predicate is quantified by a test level T. It describes the condition under which this predicate holds. Finally, we annotate a judgment with its corresponding analysis name A. We also require a judgment to be well-formed. It means that the context gamma and the guarantee B should describe behaviors that are based on the same set of resources. With BI in mind, let's look back to our two naive judgments. For separators, we really need semicolon for the first judgment and a comma for the second judgment. The second judgment is not well-formed, so we add an additional unit component to the context. It represents any behavior for the pink IRS component. Test level quantifies the level of under-approximation, and it continues to do so after analysis computation. For example, here, the test level for the guarantee of the second judgment shows that the guarantee only holds when the internal resource of the blue OBC satisfies T1, which requires that LT to be less than V0. This only holds for LN4, but not LN5. It explains why area 5 failed after composing this reused OBC with other components. Now, with those property structure judgment, our next step is to define its meaning with Kripke style semantics. First, we define the possible words as a set of action traces. With standard reduction and composition, it forms a pre-ordered commutative monoid. Then we define our Kripke style semantics based on whether a trace satisfies the behavior described by the gamma or the formula B. For the detail of the semantics, please look at our paper. Based on the semantics, a judgment gamma gives us B can be interpreted as if a trace satisfies the behavior described by the gamma, then it should also satisfy the behavior described by the guarantee B. Now we know how to structure a judgment, define its meaning. Next, we define a set of rules to reason about those judgments. The rule set is a Ginton-style sequent calculus called label BI. For the rule details, please refer to our paper. To show that our development is sound, is reasonable, we build two important properties. First, label BI enjoys Klein elimination. Second, label BI is sound with respect to our Kripke semantics. Those two properties are helpful in our framework composing different analyses. The framework works like this. Given the system structure, a set of analyses, and the goal, a proof search for the goal can be processed with the label BI rules. It takes all the analyses as axioms and is based on the Klein elimination algorithm. Similar to other calculi based on bunch implication, the proof search algorithm is not terminating. So we make it interactive, allowing hints from users. If the derivation does not exist, the output is an error. Otherwise, the proof derivation is generated. In that case, our soundness theorem guarantees the goal derived within the derivation is meaningful. We also build an implementation to automate this process. It's written in OCaml. This is a summary of our contributions I will not repeat again. There are also other work that consider under-approximation, for example, incorrectness logic. However, it composes the evidence for the reachability of bad states, aiming to find bugs, while label BI works on the reachability of good states. As for future work, we plan to fully automate the proof search by designing a terminating calculus for label BI, possibly with ideas from G4IP. And now label BI works on systems that in a dank structure. We also plan to support a system beyond this by incorporating inductive reasoning principle with test level invariants. The idea is very similar to the resource invariant in separation logic. That concludes my presentation today. Thanks.
Thank you for talk. I think the intuition that treating separately with same resource and different resources, not only for under-approximative analysis. So I wonder why you stick with under-approximate analysis.
Gotcha. Thanks for the question. I should clarify that. Because you want to say like over-approximate analysis also should be composable, right? Yeah, they are composable. There are some previous work like relay guarantee reasoning that can support you to compose over-approximate analysis. So our novelty is that we included this under-approximation part to make it composable. Yeah. Does that answer your question?
Maybe we can take this offline.
Okay.
Yeah. All right, switch we're slightly